The other thing to note too is that there's a very large range of rate enhancements, and part of that has to do with a very wide range of efficiencies of enzymes, but it also tells you, indicates how varied the uncatalyzed reaction rates are as well. So there's a lot going on in these numbers, but basically we're just showing you the huge range of activities of enhancements, and then again to how extreme some of these enhancements can be. Okay, very trivial kinetics. I'm not going to go into depth defining reaction kinetics for you, but we've got our familiar equilibrium constant, right? We can describe the concentration of reactants and products, or substrates and products, at equilibrium, and we can relate that to free energies. Likewise, we can think about the reaction, the activation energy barrier size in terms of a constant, and that's k, the reaction rate, little k, the reaction rate constant. So e to the delta g double dagger tells us something about the magnitude of our rate constant. But reaction velocities then are going to depend on the rate constant and the substrate concentration. This is one way to write a particular kind of rate, kinetic rate equation. So in this case, we write it into a constant. We use K to calculate a concentration-dependent reaction rate. There are many others besides this first-order reaction rate, in which the reaction rate solely depends on the concentration of substrate. Right, so again, orders of chemical reaction. In this case, when we're just looking at the change of product over time, and that tells us what the rate is the same as the rate constant. This is a zeroth order reaction. Doesn't depend on the concentration of the reactant. First order reactions, on the other hand, depend only on the concentration of substrate, and second order reaction, then you add more terms to this equation, and the kinetics of the chemical reaction are that much more complex. Again, as we have done for other kinds of problems, we turn to a simple phenomenological model for describing reaction kinetics. Enzyme plus substrate, or E plus S, goes to something called an enzyme-substrate complex. And here's where the interesting stuff occurs. The chemistry occurs here, and then we see this complex fall apart and product be released. Now, you'll note here that I've drawn a double arrow here, right? The enzyme substrate complex is formed and it is broken, right? And only one direction here. So we typically do considered conditions, only conditions in which we're going to go to product and not the reverse. And that's there's several assumptions that are built into our enzyme kinetics models, and one assumption might be that we'll only consider reaction rates when there's relatively little product formed, and therefore very little possibility of going in the reverse direction. Another way to say that, I guess, is that enzyme reactions are pseudo first order. This simplifies things, right? There's pseudo first order when substrate is in large excess over product. So when does that take place? Well, let's take a second to look at some fake data. Here we're looking at the concentration of product, so that's going to change as a function of time after we initiate the chemical reaction, say by adding the substrate to our enzyme. And we see that the reaction rate changes. There's one slope at the beginning of the reaction and another slope at the end of the reaction. So this is referred to as the initial velocity, and here we say it reflects conditions wherein this favors the forward reaction. So we're not, right? So formally we should have an arrow here, but since we have no product, we're not going to go back, right? We're only going to go forward. So when you do your own kinetics experiments, you will restrict yourself to reporting reaction rates to initial velocities. But of course, as substrate is consumed, product is formed, and equilibrium is ultimately reached, and that implies that there's some appreciable concentration of product that's going to alter this unidirectional assumption. Okay, so on this slide, I've sort of tried to again clarify how we go about making our kinetics measurements. And then if you see what the measurements tell you, then we can think about going from that phenomenological ES model to a mathematical expression to help us understand that model. So first, let's again think about making kinetic measurements. So here again is that same data, right? Change of product with time, one rate in the beginning, changing rate as equilibrium is reached, and again at early times we're effectively zeroth order with respect to substrate. So there's another assumption. We can say we're effectively zeroth order with respect to substrate. Substrate concentration isn't changing. Is another way to say that. So what can we do then? Well, we can take these initial reaction rates, this initial velocities, and measure them at a range of substrate concentrations. So then our next step then is to measure those reaction rates as we vary the substrate concentration. And what we see is that the reaction velocity changes. So now this isn't product concentration changing. This is this initial velocity. Each of these data points represents an initial velocity measured at a different substrate concentration. And we see some interesting things here, just as we saw with binding curves, not to be mistaken for a binding curve, but similarly we see that there's some saturation in the reaction rate. We'll refer to that as V max, right? So at a certain point it doesn't matter how much we increase the substrate concentration, we're not going to reach any higher velocity. And but again, those Vmaxes aren't necessarily very telling. Instead, what's telling is the half of Vmax, and that is one way to define the Km, or the Michaelis constant. That is the substrate concentration at which the initial velocity is 1/2 of Vmax. We'll see that there are other ways of defining that, but it's convenient to define it that way in the beginning. And then we see that at low substrate concentrations, the reaction is first order with respect to substrate, so the rate is increasing as we increase substrate concentration, but second order overall, right? So we have to also consider product concentration. Now, yes, so here again, the point being that we're zeroth order because the substrate concentration is effectively constant. Here we see that initial velocity depends on substrate concentration, and at high substrate concentrations, the reaction becomes zero order with respect to substrate, right? Again, substrate concentration changes, but the velocity doesn't change, so we'll call that zeroth order. Second order overall. Now, Km can be a metric of substrate affinity. Your book says otherwise, and I absolutely agree with that. But but it is useful to think about it in terms of substrate affinity. And this is an example that I've shown you previously for ligand-induced conformational change or induced fit binding, hexokinase. But let's make sure that we're clear. This assertion that I'm making is that we can think about the relative affinity of an enzyme for relative substrates only when kcat becomes the rate limiting step of the reaction. That is, when kcat is the slowest part of the reaction. I hope that makes sense when you think about what determines the overall rate of the reaction that you observe. That's going to be the rate limiting step, the slowest step. Everything else is faster, right? And that's the bottleneck. So if we satisfy this condition, then Km can be the metric for relative affinities for substrates. And interestingly, when we look at the two different hexoses, glucose versus fructose, right? One is an aldose, one is a ketose, right? We have CKMs that are on the order of 0.05 millimolar for glucose, and 1.5 millimolar for fructose, right? So we're talking about, what are we talking about here? A factor of 20 or 30, right? Greater than, 20 or 30 fold greater in the case of glucose, higher affinity, apparently, as measured by Km, than for fructose. Now, what does this mean? Well, this kind of tells us what substrate might best induce that conformational change, right? So glucose providing the proper set of interactions that drive this protein to shift to one domain to shift closer to the other, and fructose doesn't satisfy those, and so we have to add more substrate in order to get the binding event to occur. So that selectivity can be determined again under certain conditions by the Km. Remember that our simple definition of Km is just that concentration at which the reaction velocity is half max. So we see that at very low concentrations for glucose we're at half max, and we have to go much higher in order to excite the same reaction velocities. So back to our phenomenological model, though. I've shown you what the data look like, and I've shown you that there's a couple of things that you can see from those initial velocity measurements. That is, we can see that the reaction velocity reaches some maximum that's characteristic, and we know that there's some half maximum value that's characteristic for particular kinds of substrates. How can we derive a model that describes this ES phenomenon? Well, let's start by assigning reaction rate constants to each of the reactions that are described in this phenomenological model. So here we have K1, that's the formation of the ES complex from E plus S, forward reaction there. K minus 1 is the reverse reaction, that is the non-productive disassembly of the ES complex. So K1 and K minus 1. K2, also known as Kcat, is the productive disassembly of the ES complex. And again, we could have a K minus 2, but we'll assume that we don't by defining conditions in the appropriate way. So, what next? So ultimately, we want to get to a mathematical expression to describe this initial velocity versus substrate data. Again, we see a rectangular hyperbola, right? This is a way to write down a rectangular hyperbola algebraically, and if we could substitute terms for our rate equation into that, then we can see that we can define the reaction velocity in terms of Vmax, Km, and substrate concentration. Those are the only three things that we care about in this plot: Vmax, Km, substrate concentration. And I'll just skip to the end and say that the ES model describes the data for some enzymes, certainly not for all enzymes, but for very simple systems, we'll call them Michaelis-Menten systems, the model works